All right. Yes.
So we're delighted to have Courtney Dressing giving us a talk today. Courtney managed to leave Boston despite the storm of the century. She's a finishing PhD student at Harvard, working with Dave Charbonneau. She's a particular interest in small planets around small stars, I would say. And we'll show you some of the very nice results she has obtained already on this topic. She's on the job market. She's doing very well. She's already saying no to a number of places, to give you an idea. And we're trying to have her come here. And she very gracefully, for visiting us, has accepted to give us a talk. Thank you.
Thanks, Christian. As you probably guessed from the title, I have two main things to tell you today. The first part of the talk is about planet occurrence for small stars, largely from Kepler. And then in the second half of the talk, I'll talk about characterizing small planets in detail, concentrating on planets orbiting very bright stars. So in the first half, we'll begin by looking at the Kepler M dwarfs and coming up with better properties for them. I'll then talk about a pipeline I wrote to try to find additional planets in the Kepler data and to explicitly measure the sensitivity of our pipeline to small planets and longer period planets. In the second half, I'll talk about AO imaging of Kepler target stars to see which planetary companions might be larger than we thought because of dilution from nearby stars. And then I'll talk about the planet Kepler 93b and a mass measurement we made with HARPS North, and also the implications for the masses of other small planets. At the end, I thought it would be fun to also give you an update about the TESS mission and some of the work we're doing with HARPS North to follow up discoveries made by K2. To begin, as Dave Charbonneau probably emphasized when he was here recently, we know that planets like the Earth orbiting stars like the Sun are notoriously hard to detect. An Earth-sized planet in the habitable zone of a G-star transits only once per year, which is not very frequent, especially if you're on a 5-year PhD and you would like to see multiple transits during your PhD time. It's also not very deep, and it's unlikely to occur. You have a 0.5% chance that particular planet will transit. And if you do have a transit, you're probably going to need to see multiple transits to add up the signal to noise necessary for you to actually detect that planet. That means that even for Kepler, which is remarkably precise, the 4-year mission was not sufficient to enable a robust measurement of the fraction of Earth-sized planets orbiting G-stars. But fortunately, there's a way you can get around this. If you look at smaller stars, for instance, if you look at an M4 star, the planet is much bigger compared to the star. The transits are more likely to occur within the habitable zone because the habitable zone is closer in. And when the transits do occur, they're very deep. So that means that it's a lot easier to measure the fraction of M dwarfs with potentially habitable small planets than it is to measure the fraction of G stars with potentially habitable small planets. That's a star spot.
So they're bigger star spots.
Yes, right. So the downsides of M stars, of course, are that the stars are more magnetically active. And it's interesting to contemplate what life would be like on a planet orbiting an M dwarf. You might need to have a strong magnetic field to shield the planet from radiation from the star. The planet might be tidally locked. You might have strange climate effects. So it raises a whole bunch of very interesting theoretical problems. And then the other interesting thing about M dwarfs is that, as we know from the IMF, M dwarfs are common. If you have a particular sample of stars, odds are 75% of them are M dwarfs. And if those M dwarfs have planets, that might imply the majority of potentially habitable planets in the galaxy actually orbit M dwarfs. The Kepler mission wasn't focused on M dwarfs, though. Kepler was focused on stars like the Sun, which meant when they constructed the Kepler input catalog that gave the lists of all of the target star radii and temperatures, they used methods that were very well suited for characterizing sun-like stars and not so well suited for characterizing M dwarfs. The first part of my PhD was to look at the Kepler input catalog and revise the properties of the smallest stars. We looked at the photometry in the catalog, and we also compared the photometry to the Dartmouth stellar evolutionary models, and that allowed us to get a better handle on the radii and temperatures of the stars. The reason why we did this is shown here. This is a plot of the radii and temperatures of the Kepler M dwarfs we considered in our 2013 paper. The gray points are what we would expect. Those are models for low-mass stars. The blue points are the values those low-mass stars originally had in the Kepler input catalog. A lot of them fall into no man's land, where the star is just far bigger than one would expect for its temperature. It's not a giant, it's not a dwarf, it's somewhere in between, where those parameters were determined by just averaging the best fit dwarf and giant models, which is not a real star. By construction, we ended up by matching the photometry to these gray points we ended up with revised parameters for the low mass stars, and they now fall nicely on these red tracks. So the first step was to figure out how big and how cool are these stars actually. The next thing we did in 2013 was compute the planet occurrence rate. We wanted to figure out how common small planets were around low mass stars. For this talk, I'm going to refer to planet occurrence as just the number of planets divided by the number of stars. So that's the mean number of planets per star, rather than the fraction of stars which host one or more planets. There are two important things to consider when computing the planet occurrence rate. You can't just take the number of stars in your sample and the number of planet candidates you found. The reason for that is that first, you can't find all the planets. Some things are just too small, or their orbital periods are too long, that they might never transit, or if they do transit, you might not be sensitive to detect the transit. The second consideration is that not everything that's reported as a planet candidate is actually a planet. In some cases, particularly for big things, they might actually be false positives, where they're two eclipsing binary stars that are then blended with light from your target star, causing you to think that you have a planet when really you just have a triple star system. Now in 2015, Dave Charbonneau and I have revised our analysis of the planet frequency for low mass planets around M dwarfs. We've made a bunch of improvements to the 2013 analysis, and I think the largest of those improvements is that I wrote a pipeline to look for planets in the Kepler data. Previously, when we estimated the occurrence rate of planets, we used an assumption that Kepler would have found any planet with a cumulative transit signal to noise of 7.1 sigma or higher, and nothing below that. Now what we've done is we've actually taken a bunch of fake planets, injected them into Kepler light curves, and seen which planets were detected and which planets weren't. That gives us a better handle on regions where we might have missed planets that were either too small or too long period. And we can then refine the occurrence rate of potentially habitable planets. Some of the other things we've done are that we looked at the wonderful wealth of follow-up observations made by the whole community to figure out which systems are actually eclipsing binaries, or which systems are more likely to be real planets because they actually have radial velocity masses. With our pipeline, we actually do a pretty good job finding the same things that the Kepler team found. This is a plot of planet radius versus period. And in the green box is the region where I'm going to tell you planet occurrence rates soon. The colored points with error bars are planets that we found. Within this box, the Kepler pipeline found all of these things, except for 2. And we found all but 7 of the objects that the Kepler pipeline found. For the most part, the objects we miss are down here. So they're very much on the cusp of detection. And it's OK that we didn't find everything. The real goal of writing our own pipeline is to really know, with the same pipeline, how sensitive are we to small planets, and also how many things do we recover.
7.5 sigma, is it what the Kepler uses?
Yes, that's what they used. And it was designed because they wanted to have one statistical false positive during the entire mission. Right. I mentioned before that you could have systems that were not really planet candidates. They could be blends. These are 2 potentially habitable systems where originally, with the 2013 data, we thought that those could be Earth-sized planets in the habitable zones of their host stars. And then thanks to adaptive optics images by Dave Chiardi and Ron Gilliland, this one's from HST, this one's from Keck, they found that those systems are actually multiple stars. In the case of KOI 2626, there are 3 stars there, and depending on which of the 3 stars the planet orbits, it might still be habitable, or it might be much bigger and much hotter. In the case of the 1422 system, that's actually 5 planets. And it's true that it could still be a habitable planet system. It's just the planets we thought were habitable are actually too hot, and the ones we thought were too cold might actually be the right temperature. So the whole point of this slide is that before you get too invested in any one particular planet candidate, it's a really good idea to go after an AO image to really characterize the system.
Multiple stars all low mass, or why did they look like M stars before?
They are all low mass. So in the 1422 system, I think one of them is significantly brighter than the other. And you could barely tell that there was another star there.
Is it the case that the studies of the false positive for the Kepler sample as a whole is not focused on M dwarf, and so that actually it might be different, the frequency at which we get false positive for M dwarf?
It might be different. Francois Frassen had a nice paper in which he looked at the false positive rate as a function of planet size and also slightly as a function of host star temperature. And there are regions of parameter space where the false positive rate is very different than the canonical 11% value sometimes quoted. And the M dwarfs are particularly tricky, partially because those stars are so much fainter that there are many more things that could be contributing to light in the aperture. And one of the false positives that's actually quite common is to have a larger planet, something that maybe is Neptune or Jupiter sized, that's transiting a planet, or transiting a star, and you have another star there as well, and you just record that as an Earth-sized planet. And it might actually be something that's a little bit bigger. The way we decided to measure the sensitivity of our new pipeline to planets as a function of radius and period, or as a function of radius and insolation, was to generate a grid of 2,000 possible planets for each star in our sample. Those are represented by the diamonds here. The next thing I did was for each of these transiting planets, I computed a model light curve and asked how different is this model light curve from a straight line given the precision of our data. For some cases, the ones down here, you really couldn't tell the difference. It would be statistically undetectable as a transiting planet. So we knew that we were not sensitive to things in this regime. There are also some planets where you have a slight detection, but once you fold in the fact that you have to detrend your data and you have to remove stellar systematics and spacecraft systematics, the signal's no longer detectable. So that rules out this parameter space down here. And then finally, for things that were just along the cusp, I did 50% of the objects that are just barely above that detection threshold and ran them through our full detection pipeline, starting with a box-fitting least squares periodogram, finding the peaks in that, and then trying to test to see whether transiting planet models would fit the data better than a straight line model. In that case, we found that the objects in yellow are detected and the objects in red are not detected. This is just an example for one star, this star here, but we did this for all of the 3,000 odd stars in our sample, and we're able to plot, as a function of the difference between a transit model and a straight line, how likely are we to find that particular planet. That allowed us to extrapolate this red line, which we then went back and said that for this point here, we knew what the delta chi-squared was. We could assign a probability we would find that planet. We filled in the entire parameter space. And then for each star, we can produce a map of search completeness, where dark colors are low completeness. It's very hard to find a short period Mercury-sized or long period Mercury-sized planet. Very easy to find a hot Jupiter. And then we can also do this for all of the stars in our sample together. So as you can see, this is a plot of search completeness. Yes?
No, not an expert, but 90, sort of upper left are also like 91%.
Yes.
Why is it that closer to 100?
It's mostly because of time baseline incompleteness, that we are missing some transits. In some cases, it's also because this pipeline is designed to try to find the small things and to remove systematics. So in some cases, really, really big transits, things like John Johnson's giant planet Radium dwarf might actually get removed by the pipeline. Good question. So looking at the full sample, we end up with this map of search completeness. We're up at the top, we're at 91%. Down here, we're at 0. And along this ridge here is where I'm really interested, because the habitable zone for these small stars is really right about here, right where completeness changes dramatically as you go from Earth-sized planets to 1.5 Earth-sized planets. If we look at the plot of all of the planet candidates we found, we end up with this distribution. And here the shading in the background shows the errors from our Monte Carlo fits to the transit light curves. And I've smeared out the errors in the period, because that's actually something we determine very, very well. If I take this smeared out map of where we find planets and divide it by our map of search completeness, we can get a map of the planet occurrence rate. Here the light colors again are lots and lots of planets, and the dark colors are very rare planets. Down here in the corner, that's a region where the search completeness is so low that we don't feel like we have a good grasp on the planet occurrence rate. One of the numbers you might be interested in is if we make this into a version that's easier to read, you can tell that for planets that are Earth-sized with periods of less than 50 days, we find that there should be about 0.6 of those per small star. For things that are super Earth-sized and periods less than 50 days, we find that are about 0.5 per small star. So those little planets are very common.
Can you tell how you get those numbers? You add
Yeah. Right, so from here to here?
No,
or
the numbers you were saying, were
they yes.
You basically integrate
right.
to the left?
Right, so what we did is we divided up the search space into boxes, and then we can quote the planet occurrence rate within a particular box by just saying these are the number of objects we found and the fraction of objects within that box we were sensitive to.
Oh, no, the percents are under.
Yeah, the percentages here are the detection completeness. So down here, only 35% of planets are detected, so there's a large correction for search incompleteness.
So does the Poisson
On this plot, no, but in the table in the paper, yes. There is a large Poisson error, especially on the right side of the plot.
So when you're signing 5%, 6%, what's kind of Poisson error?
So for the 50 days Earth-side planet quote, that's 0.6 plus or minus 0.06. If you go out to 100 days, it then turns into 0.7 plus or minus about 0.1.
So it's really small.
Yes. And then this is just another representation of the size of the planet on the bottom versus the number of planets per star on the left. And each of the colored lines is a different orbital period range. And as you've probably heard from many people before, we now see that small planets are much more common than large planets. And then as you go to longer periods, you actually see more planets. So things that are really close in and big are rare, which might be a sign that those close in big planets are getting photoevaporated and ending up as small planets. We can also look at things in terms of the insolation flux experienced by all of these planets. This is the population of planet candidates we detect. And these colored lines here show two different choices of the habitable zone. The green lines are the conservative boundaries from the Caporato et al. Study that try to take into account how cool could you make a planet by adding on additional carbon dioxide, and how close to a star can you push the planet before you have a runaway greenhouse effect. The purple lines are empirical limits based on the assumption that Venus and Mars could have been habitable in the past. This is the planet occurrence rate plot, then as a function of insolation, created the same way we did the period versus radius plot. And if we grid that up, you can see that within the habitable zone, so regions that are roughly here-ish for these M-dwarfs, for an Earth-sized planet, between those conservative habitable zone boundaries, we get about 0.16 planets per M-dwarf. And now the errors are quite large. It's plus 0.2, minus 0.07. For super-Earths, we get something like 0.09 per star. If you use an empirical limit of Earths that could be at Venus-like distances or out to Mars-like distances, it's 1 out of every 4 M-dwarfs having a possibly habitable Earth-sized planet. So the errors are still pretty big, mostly because this is a region where we have low search completeness. We're finding 40% to maybe 80% of those objects. But the important thing to take away is that these numbers are actually pretty high. It's not 1 out of every 10,000 M-dwarfs. It's 1 out of every 4. Maybe 1 out of every 2, maybe 1 out of every 8. But it's a number that means that we should be able to find a planet like this around a relatively nearby star and then characterize it in detail. Here's another way of looking at the planet occurrence rate as a function of insolation. Here, the colored lines are different radii of planets. And one thing you can see here, and of course bear in mind that the errors are still a bit large, is that at high insolation, so things that are really close to their star, very, very hot, we see that the bigger planets, here in brown and gray, are slightly less common than the really little planets in orange and red. That could be a sign that the orange and red planets are the leftover cores of gray and brown planets that have been photoevaporated. That's something that's open for debate. Yes?
In your previous figure, why are those lines crossing?
Right here?
Yeah, why are they, yes, for example, the first two they're crossing at about 10, or the other ones are crossing?
Right, so in theory, it could be that perhaps once you get that far away, you're less likely to be photoevaporated. And then if they form at the same rate, and then some of them migrate in and lose the atmosphere, maybe that's a sign that you're actually decreasing abundance.
I'm saying, so that's what you're saying. The data says that that's accumulated. So for some reason, it's a little bit easier to detect, say, a 1.5 Earth radii than a 2 Earth radii when they're really, really close, which is, to me...
Oh, so this is just the cumulative planets per star. So this is the, after we correct for search completeness, how many planets are actually orbiting these stars. So it's still easier to find the 2.5 Earth radius planet. Does that make more sense?
No, I still don't understand why they cross. I would have imagined that if you go to larger planets, then it's easier, and then the rate at which they exist is comparable, unless there's something else there. I don't know.
Yeah, I think it's an interesting question. All right, so that was the first part. That was planet occurrence around low-mass stars. We see that small planets are common, and that small planets that are Earth-like temperatures might be more common than we might have previously expected.
Can I ask you a question?
Yeah.
Now that you have such an M-dwarf statistics, have you tried to compare against Utah stars?
We have. Part of the challenge is that the habitable zone for M dwarfs is a region of low search completeness. For G dwarfs, it's even worse. So you have to make some choices about the functional form you assume for the planet occurrence rate as a function of orbital period. If you assume that it's flat in log period, you get a number that's about a factor of 2 lower than what we find for M dwarfs. The Pettigrew et al. Result that's sometimes quoted is 22%, and that's for a slightly bigger box in the habitable zone. If you use the same size box, they get something like 11%, which is roughly half.
I'm interested in saying how does that come about? Like, you know, like the same, say, centimeter axis.
Right.
How's the occurrence rate around M-dwarf compared to G-type stars? This kind of comparison, would that be possible?
That is something you could do. There's an interesting paper about the planet occurrence rate scaling with the original debris disk structure, that the position of the snow line, that if you scale the position of the snow line, you might actually see the same planet occurrence rates, which is interesting. Or the disk co-rotation radius for the star is also quite important. In the second part, I wanted to tell you about some of the work we've done with small planets orbiting bright stars. And the reason why bright stars are nice is that they're very easy to observe from the ground. One of the things we did is that we looked at low-mass stars that might possibly host Earth-sized transiting planets. Some of these planets ended up not being so Earth-sized once we saw that they had other stars nearby. Here's just a gallery showing the stars we looked at that happen to have companions within 2 arcseconds. Whoa. OK, PowerPoint is restarting. Sorry about that. There we go. All right, so these are companions within 1 arcsecond. In some cases, the companions are much fainter than the target star. In other cases, they're roughly equal mass. In the worst case scenario, if you have 2 stars that happen to be equal mass binaries, you would end up with a factor of 1.4 in terms of the additional light in the aperture. In other cases, if you have 2 stars, you could have a case where the planet orbits the target star, and there's a little bit of dilution from another star. That has a very slight change on the radius of the planet. But if the planet actually orbits this little star, and you thought you were targeting this big star, the planet could actually be much larger than you initially thought. We haven't yet tested which of these stars are physically associated and which ones are background companions. But from other studies, we've seen that if the stars are really close together in the sky, odds are they are physically associated. We have some with companions within 2 arcseconds, and a handful with companions within 4 arcseconds. And the main takeaway point from this section of the talk is that for the observations we did on Aries at the MMT, we were sensitive to companions that were roughly 5 to 7 KS magnitudes fainter than the target star. So here's KS magnitude difference, where the brighter companions are up at the top, fainter companions are at the bottom. And we have distance from the primary along the bottom. And the colored lines are for 3 particular systems. What is our search completeness limit for that star? And for those 3 systems, the companions we found are indicated by these stars. And in this plot, you can see that there's a huge difference between the completeness for these stars. And that's just because this particular star was fainter than these 2.
How many stars were there?
87 stars.
These are stars with planets?
Most of them had planets. We were working from the early version of the Kepler team planet candidate list. And 3 of them ended up not actually having planet candidates by the time the paper went to press. But we tried to look at the ones that were small that hadn't been previously observed. So this is not an unbiased sample of planet candidates. Something that Dave Charbonneau might have told you about earlier is our search with HARPS North to try to measure the masses of small planets and figure out what this means for the formation of rocky planets. To do this, we're using the Telescopio Nacional Galileo, pictured here, which is on the Canary Islands off the coast of Africa. And the instrument in particular is HARPS North, which is built by Francesco Pepe and is part of a large consortium. It's an international effort. And at the CFA, some of the main players are Dave Latham and Dave Charbonneau, Lars Bukov, and Mercedes Lopez Morales, and now John Johnson. So all of them are actively involved in this. And I've done the small part of working on the single planet, Kepler 93b. The reason why we were interested in this planet is that about a year ago, Sarah Ballard and her collaborators conducted an astroseismic investigation of the star Kepler 93. That enabled them to really nail down the measurement of the radius of Kepler 93b, the planet. As you can see here, they got a value of 1.48 Earth radii, and they had a precision of 120 kilometers, which is very impressive considering that this planet is quite far away from us. The advantage of having such a well-characterized star and a well-characterized planet is that with a decent mass measurement, you can actually have a pretty tight constraint on the density of that planet. We went after this system with HARPS North, and we also considered some archival observations from high-res on Keck. Here's a plot showing the RVs versus time. So this is radial velocity versus time in barycentric Julian date. Probably can't read the axes from the back, but that's fine. All I want you to see is that there's a long-term linear trend. That linear trend indicates that there's another star or planet in the system. We have AO images of this star, so we can place limits on the mass and separation that we could have. So here we have mass versus separation. We can rule out the green region from the radial velocity trend and the blue region from the Keck adaptive optics, leaving the parameters of that companion somewhere within here. There's some slight indication that perhaps this linear trend is changing shape. So if we get 1 or 2 points observing the system next year, we might be able to say something more about the third body in the system. If we remove the influence of the companion, we end up with a nice phase-folded plot of the radial velocity showing the influence of Kepler 93b. And the mass we infer for this object is 4 Earth masses. Combining that with the radius of 1.5 Earth radii, we find that it seems to be rocky. And just because I'm from the HARPS North collaboration, we're really excited to see that our residuals look really good on this system. This is the histogram of residuals as a function of meter per second. And here in dark blue, we have the HARPS North residuals, which are nice and fairly Gaussian. We have the high-res residuals, which are shown in light blue and slightly broader. HARPS North is on a 3.6 meter telescope, which is much smaller than Keck, but we're showing that we can compete with the big guys. One reason why we're interested in this system in particular is that there aren't that many planets with masses and radii that have been well measured outside of our solar system. Here are a bunch of theoretical models from Li Zhang, a graduate student at Harvard. And all of these lines indicate what mass and radius we would expect for a given planetary composition. And Jonathan Courtney could show you his own compositional models. So the point here is not which particular set of models we use, just that we can do this now. We actually have a decent sample of planets outside our solar system with precisely constrained masses and radii. There are also many planets with less precisely constrained masses and radii, and those provide an additional important constraint on the compositions of small planets. But just for clarity, I'm only going to show you systems for which we have the mass and the radius measured to better than 20%. One of those systems is Kepler 36b, which is a case where we actually have a photometric mass using transit timing variations. Corot 7b is a small planet from the Corot mission. Kepler 78b, a nice example of collaboration between the HARPS North team and the high-res team. Both teams looked at this planet individually, reduced the data, and ended up with consistent results, demonstrating that this very short period planet is rocky. We also have Kepler 10b, which was reanalyzed last year by Xavier de Musque using additional observations from HARPS North. And then I measured the mass of Kepler 93b with the help of everyone in the HARPS North consortium. As you might have noticed, if you look between the all rock and 50-50 rock iron line, it seems like all of these objects could be consistent with a single 2-component model. And when we looked at Lee's set of 2-component magnesium silicate and iron models, we found that there is a model that fits all these planets nicely. And that model happens to be the same model that you would use to describe the Earth and Venus. That suggests that perhaps all of these planets are formed from basically the same ratio of iron to magnesium silicate. That's not true for the larger planets. As you can see here, the larger planets show a lot more scatter in radius at a given mass, suggesting that above about 1.6 Earth radii, which is the limit that Leslie Rogers proposed as well, and that Lauren Weiss talked about in her paper with Jeff Marcy, it seems like at that point you really require some volatiles. There are interesting objects that appear in this region of the plot. If you look at planets from TTVs, or planets that have less tight constrained on the masses. And one thing we're actively investigating right now is what happens if you assume that the TTV planets have the same masses as the planets in the system. Can that actually work? Or do you find that you can't reproduce the TTVs if you assume that those planets have rocky compositions? Another question we're asking is, we have a lot of systems where we've looked at them with HARPS North, we have small planets, and we've tried to measure the masses of those planets, but we're not at 20% precision yet. Are those planets still consistent with having a rocky composition, or does the fact that we haven't measured their mass yet indicate that they must be fluffier? So we're trying to see whether this is the full story or whether there are unanswered mysteries. And given that it's exoplanetary science, there are probably many more complications that will be later revealed as we get more and more planets with precisely measured properties.
How involved is it to get the mass? For
those? So most of these, a lot of nights. For Kepler 93b, we had about 80 observations. For Kepler 78b, I think it was maybe 60. So the nice thing about HARPS North, though, is that the HARPS North collaboration... Oh, observations. So those are about an hour per night. But we have 80 nights per year. So a lot of these are 2 seasons of effort with HARPS North. And in the future, we are going to be spending a lot of that time on K2 and Kepler planets. So we should be able to get another 3 planets on this diagram every year between now and whenever our GTO program ends. So that's actually a great segue to the future, which is prospects for the detection of Earth-like planets, both from the ground and from space. As you know, we would love to be able to find a planet that looks like this and possibly take a picture of it. In 2018, we have the James Webb Space Telescope, which should allow us to get a better handle on the properties of planets orbiting nearby and possibly low-mass stars. We also have a bunch of instruments from the ground, and particularly here in Toronto, the TMT is pretty exciting. However, the planets found by Kepler orbit stars that are in general too faint to be studied in detail with these instruments. We really need a population of small planets around brighter stars. And there's a solution for that. There's a whole bunch of missions that are targeting planets around small stars, bright stars, or nearby stars. I'm going to tell you more in detail about K2 and TESS. K2 is an attempt to use the Kepler spacecraft, even though 2 of the 4 reaction wheels are now no longer operational. This complicated slide from NASA is a schematic of how K2 works. And the gist of it is that K2 can point stably along the ecliptic because the solar wind actually balances on the spacecraft. So if you point in a particular field of the sky, you have about 80 days where you can look stably before you have to move on to the next field. And the time duration of 80 days is limited by how long you can keep the light on the solar panels. K2 is proceeding very well. This is an initial plot of the K2 performance. This is precision versus Kepler magnitude. And in red are the original Kepler mission. So 12th magnitude stars had about 20, maybe 40 parts per million precision over 6 hours. With K2, the points in blue show the K2 fine point test. So initially it was coming in maybe 5 times what we measured with Kepler. But Andrew Vanderberg, a brilliant grad student at Harvard, who will be on the job market sooner than anyone realizes, found that you can actually do even better. If you look at the position of the stars on the pixel, and you correct for that using a self-flat fielding method, you can actually get the precision of K2 down to approximately half that of Kepler. So here we have relative brightness versus time. The blue dots are the out-of-the-box K2 measurements. You can see there are very jagged features where the brightness of the star seems to change quite frequently. And the timing of these jagged features is linked to when the spacecraft fired its thrusters to stably point again. Andrew was able to remove this effect and end up with this nice, smooth yellow line showing that for the most part, K2 will be almost as sensitive to planets as Kepler. Andrew also found the first transiting planet in the K2 data. Here's an example of the transit light curve here. And then in collaboration with the HARPS North Consortium, they measured the mass of the planet. And that was one of those objects in the upper right that was consistent with being more volatile rich. Just last week, there was another exciting announcement from K2, the first multi-planet system. Here we have the light curve from K2 versus time, and all of these dips are transits. And the dips actually correspond to 3 different planets. One of them is 2 Earth radii, has a period of 10 days. The middle one, with the transits marked in blue, is a little bit smaller and has a 24-day period. And then the third one is 45 days and is 1.5 times the size of the Earth. That planet has been creating a lot of buzz because it's right on the very inner edge of the habitable zone for that star. So this planet right here might actually be one of the first targets we study with James Webb, or possibly with the TMT. And it would be very interesting if we not just had radii for these planets, but also had masses. So we've started with HARPS North to observe this system. We currently have about 12 observations. The high-res team has a run starting in about a week, and they're going to get observations of the system. So by next year, we should actually have a good handle on the mass of this planet, maybe this planet, and if we're lucky, we might solve the whole system and get this one. We might also discover that there are additional planets that were not seen to transit in the K2 data. This is only the beginning. That's what we can do with K2, but beginning in 2017, we'll have TESS as well. And TESS will conduct a full survey of the entire sky. Just to put things in context, this is the K2 fields. So here we have just all the fields of the ecliptic, where each of these is roughly 80 days of coverage. And then with TESS, we're going to do the rest of the sky, everything but the ecliptic. TESS has 4 cameras, so 1, 2, 3, 4. And they're set up so each of the 4 cameras points in a different part of the sky. One of the cameras is always pointing towards the ecliptic pole. The other 3 point farther down. It'll look at one strip of the sky for 27 days, and then shift focus a bit and do the next strip of the sky. And move all the way around to do the northern sky in 1 year, and then flip over to do the southern sky. At that point, the spacecraft will probably repeat both of the hemispheres, or maybe flip sideways and study the ecliptic. It hasn't been finalized yet, but the rumor is that we should have 4 full years to do the TESS mission, not just the original 2. With TESS, we expect we should be able to find dozens of Earth-sized planets and hundreds of super-Earth planets. This is work done by Peter Sullivan, a former grad student at MIT who's now at JPL. Here is the number of planets we expect TESS to find versus size category. And here in red are all of the things found around designated TESS targets. TESS operates kind of similarly to Kepler in that you define an aperture around your target star and you download only the pixels in that aperture. But in the case of Kepler, we had long cadence observations every 30 minutes and short cadence observations every minute. For TESS, your typical star will be downloaded once every 2 minutes. And we'll take an image of the entire field, every single pixel, not just the ones you've selected, and download that every 30 minutes. So there's a great possibility for ancillary science with TESS, that you could actually discover a supernovae on the ground and then realize that, oh, TESS was looking in the same region. And then you would actually have a light curve of that supernovae just by serendipity, which would be great.
Courtney,
Yes?
going back to the cross-fit planet, the planet C, the one that is 45 days.
Yes.
That cannot be found by TESS, or you can find one. There's only one transit.
Right.
So knowing that actually you were dealing with your planet might be much more an issue. Is that interesting?
It is actually quite tricky, because if you just had a segment of this light curve, you might not necessarily know that there are multiple planets. You might see 2 transits of 2 different planets and not realize it wasn't the same planet repeated. For TESS, one of the interesting things that Peter did was simulate where these planets would be detected on the sky. So that's this here. All the red points are planet detections. Up near the pole, you actually do have the ability to see longer period planets and to differentiate cases like that. Down near the ecliptic, you're more likely to be confused. And you're probably more likely to only find planets that have periods of 10 days or shorter. So it's a definite concern. Another thing with the advantage of the full-frame images from TESS is that because you're downloading all those extra pixels, you're actually sensitive to giant planets around stars you didn't plan to look at originally. That's what all the blue bars are. So the red bars are the yield from actual targets. The blue bars are the yields from everything else in the full-frame image. Here, the giant planets are actually dominated. There are 15,000 things that just happen to be on these pixels you've downloaded, compared to 130 giant planets found in the designated targets. There's also a bit of a challenge, though, because here we have eclipsing binaries, background eclipsing binaries, and hierarchical eclipsing binaries. And those are going to be a major source of false positives for TESS. Here's a distribution showing how the radii and periods of the planets found by TESS compare. So here you can see the histogram of periods, and here are the radii. And the big thing is what you would expect from Kepler, just that you're more likely to find little planets in shorter periods and bigger planets at longer periods, where most of the TESS detections will have periods of 10 days or shorter. Some of those might actually be small planets orbiting in the habitable zones of their host stars, just like that 3-planet system from TESS. Here we have, from K2. Here's insolation, and if you were to draw a generous habitable zone between twice and half the insolation received by the Earth, you end up with about a dozen small objects that could be in the habitable zones of their stars.
So is that 60-day period, how long you point at one strip?
So you point at one strip for 27 days, but because the strips overlap near the pole, you actually observe for about 350 days at the very pole. And along, as you go down, all of these colored regions show regions where you have more than 27 days, but less than 350. So you have a narrow part of the sky where you have a much longer coverage. And that's actually where the majority of the small planets come from. And this little black ring at the top is where James Webb will be able to stare continuously. And this is all duplicated in the southern hemisphere.
So why wouldn't you find anything beyond 50 days on the next slide?
It's mostly because there's a constraint placed in some of the simulations. This is a paper that'll be out soon. And in the paper, they do mention some single transit detections, but for the most part, they require that you see 2 or even 3 transits, just to reduce the false positives. So here, the dark gray are things you see transit more than once. The light gray are things you see transit once. And then you would have to invest significant resources, perhaps the Mirth telescope array in Arizona or Chile, to try to figure out how often those planets actually transit. Yes?
It's a little off topic, but not really. If 4 years was a done deal instead of 2, would it make a lot more sense to just double all the, instead of 27 days, just do 54, rather than doing north-south and then going back to north-south?
Right. I think there's actually engineering constraints for the 27-day period. I think you can stretch it out a little, but not too much, because the way the test detectors are designed and the way the baffling is built, you have a limited sun avoidance range. So you can't actually look too close to the sun. I think they did look into changing the test month from 27 days to something else, but it's in a 2-to-1 resonance with the moon, so it actually is 2 13-day periods, and I think if they were to do 3 of those, it might be too long for the engineering. It's interesting, though.
It's also the width of the field, I think.
Yeah. That's true. And that changed a bit, too. It got a bit bigger. Yeah, and they moved it up, too. Originally, there wasn't supposed to be the big gap around the pole, but now you get much more coverage. It wasn't supposed to be a big gap around the ecliptic, and now the poles have full coverage, which is nice. And here's just the prospects for radial velocity detection. This is RV semi-amplitude in meters per second versus V-band magnitude. And the region where we're doing well now from the ground is about 1.5 meters per second and brighter than 12. So there aren't tons of targets there, but there are way more than we would have before tests. And it's likely that some of these objects, if they happen to have clear atmospheres rather than cloudy atmospheres, might be very well suited for investigation by James Webb. So we've talked about planet occurrence around low-mass stars. We've seen that small planets are common and that potentially habitable planets might orbit 1 out of every 4 M dwarfs. I also told you that characterizing planets is important, that we need to know the sizes of the stars to really constrain the planet radii, and that we're now seeing indications that perhaps small planets have masses and radii consistent with an Earth-like composition, up to about 6 Earth masses. And to go back to the first point for a second, if we assume that we have the occurrence rate of Earth-sized planets in the habitable zones, M dwarfs, down to about 0.18, that implies that the nearest of those transiting, potentially habitable Earth-sized planets is only 11 parsecs away, which is pretty close. And then finally, I told you about some exciting discoveries made by K2, and I hopefully left you excited about tests and more planets we'll find that we can characterize in the future and follow up with systems like Sphiru. So thank you very much. I'm really excited to be here, and I'll be here all day tomorrow as well.
Plenty of time for questions.
Yes?
Are the original Kepler targets bright enough for tests?
Some of them are, and there have been interesting proposals to try to see if for the planets that exhibit TTVs, transit timing variations, if you can go back to them now and still measure the masses of some of those planets. But for the most part, your typical Kepler target is too faint, and the precision you would need is higher than what you will obtain with tests. Some of them, like Kepler 10, you could go back and look at.
You
Yes.
mentioned the JWST continuous observation in the circular ring.
Yes.
Are we restrained to actually that, or in other words, what fraction of the test area where you could find a planet like, let's say, the one you showed, we would have enough JWST observation time to get flower signature?
I think it depends on how patient you are. You certainly are not restricted just to that oval. You could go a little bit outside the oval. I'll go back to that just. Yeah, so up at the pole here, this tiny circle is where JWST can stare continuously. The red ring is where TESS will find planets with periods of maybe 100 days. You could probably look down maybe about here and still get a lot of coverage. You probably wouldn't be looking at the ecliptic, but if you had a very compelling planet there, you might be able to do a series of observations, but that would require a lot of overhead time to set up and point, and it might be hard to get that through the TAC.
So
Yes.
Can you go back to the mass radius curve? Where
Yes.
You take the planets that have 20% or better error bars.
Mm-hmm.
But if I remember, so you were talking about K9, Kepler 93b.
Yes.
I remember, so corrosive B jumps around.
A lot.
And I think Dave was telling me that they used there was some new mass proposal last year. Because other than that, it would move much more to the iron region. Are you planning, can HARPS North look at corrosivity? Is it in the field? I don't know.
So we're not planning to look at it. Raphael Haywood, who is a graduate student at St. Andrews, did a nice analysis of the data from HARPS in the Southern Hemisphere. And she did a great job really doing the best we can with the data set we have now. And I think it would require significant investment of ground-based resources to try to characterize it better. The star is a bit active, so one of the challenges is trying to figure out what's due to stellar activity and what's due to the planet. So it might actually be helpful to have simultaneous photometry and radial velocity observations. But it would be nice to be able to decrease the error bars in Corot 7b.
And the other one was Kepler 10b,
Mhm.
because according to the data that I have, it sits very close to the composition that I had for Corot 7b, which is more like a supermercury. So did you
Right.
guys revise the mass as well for Kepler 10b?
Yes, so Xavier did in his most recent paper, or maybe second to most recent paper, he's very prolific, looking at another season of data from HARPS North, in addition to the data that were used in the original Kepler 10 discovery paper. So I'd be happy to sit down tomorrow and we can see exactly how the numbers have changed. And I would love to hear your thoughts on this diagram too.
So I know that because you're restricting it to 20%, there's very few samples.
Right.
And if you increase it a little more, then there's more scatter. So
Mhm.
yeah, we should definitely.
Right. And these are all highly irradiated, so it's possible that the whole picture changes as you get farther away from the star.
Yeah, but even if they're highly radiated, I find it very surprising that they stand under Earth-like line. Of course, right, you have 1 sigma or 2 sigma.
Right.
It washes off.
Exactly. And this is also a log scale on the bottom, so it does make things look a little bit tighter.
So have you had series tell you, when you add the other ones that have either like water or humidity, tell you, oh yeah, this is a co-accretion scenario and above 6 or 7 Earth masses are done like capturing gas?
It does look like it's consistent with that picture, but I don't think it's a closed book yet. Was there a question in the back?
You had a slide that showed the future landscape for more missions, and you talked about a couple of them.
Yeah.
So are the other ones competitive, or do they do complementary things, or what?
I think for the most part, they're complementary. Some of these are radial velocity, others are transit. The other one that I know a lot about is MIRth and MIRth South, which are arrays of telescopes run by my advisor, Dave Charbonneau, trying to find planets around low-mass stars, mostly mid-Ms and some late Ms. The really nice thing that's come out of MIRth more recently has actually been a bunch of rotation period analyses. So by monitoring a lot of small stars, you're able to get a much better handle on not only the distances to those stars by using the MIRth data to constrain the parallaxes, but also the age-rotation relation. And then for some of the others, Carmenes is going to be operating in science mode soon. KOPS will be launching soon. Plato is more distant future. It's 2020s, and that's essentially Kepler on steroids. 2 very long stares of parts of the sky to find faint planets, and then a bunch of shorter duration stares. And then, of course, Spiru will try to do radial velocity observation of planets found by TESS and also by K2, and also survey to find new planets that have not been seen to transit before. So it's exciting times.
So I'm going to the test. So obviously you can look at multiple stars and it's a great candidate to follow up. how much is going to revise the statistics instead of that?
TESS is not a statistics mission. Kepler was designed to really do statistics well, and TESS, I think, will probably tell us a lot about statistics for short period planets and planets orbiting different types of stars, so stars in clusters versus stars out of clusters, stars with different metallicities and masses. But for the most part, it'll just be planets with periods of 10 days or shorter. So it won't necessarily help us with the habitable zone planet occurrence rates, except for near the poles, where you can learn more about habitable planets around mid-M dwarfs. But I think if we really want to refine the error bars on the habitable zone planet occurrence for G stars, we're going to need to wait for Plato and see what Plato tells us.
But there's enough, for example, there's enough metallicity range. I guess we know metallicity of every bright star. So
right.
Well characterized.
And once we have the Gaia parallaxes, I think that's actually going to help with the Kepler occurrence rates as well, because some of the uncertainty in Kepler is for the stars around which we did not find planets. Which of those are actually smaller than we think, which are larger than we think, and that'll allow us to refine the completeness estimate, which trickles down into the occurrence.
Any other questions for Courtney? If not, I have one which maybe is quick.
Sure.
So your pipeline you use to characterize the sensitivity of Kepler across a certain class of stars and planets. To what extent has that been, or can that be extended to cover all of the different kinds of planets and stars Kepler has looked at, and get sensitivity plots for those?
It could be definitely extended. Part of the advantage of focusing on the M dwarfs is that because we had a smaller sample of stars, we were able to inject 20 to 100 planets in the light curves of each star and run them through the full sample and contemplate the detectability of 2,000 planets per star. If we did that on the full Kepler sample, we would probably need to get supercomputer time, which would not be out of the question.
I was going to say, what's the problem with that?
Yeah, there isn't a problem with it. It's also that there have been many people looking at that issue. Eric Pettigura has a fantastic paper with a planet detection pipeline and completeness estimates. He's worked with Daniel Foreman-Mackey to think about how different assumptions you make change the occurrence rate. And the Kepler team has also been hard at work on that issue. So I figured that it might be more helpful to the community to concentrate on the problem that hasn't been studied before. Okay.
Well, if there are no other questions, two quick things. Next we'll go up and have cookies, and you can have more discussion with Courtney.